So we've seen that binary search trees can be used to implement the dictionary abstract data type. We can find, insert and delete reasonably nicely. However, we've also seen that the shape of these trees can get out of control if we just have arbitrary insertions and deletions going on. We can get big long trees with very large height, which can slow down our find operation, for example. Suppose we want to keep the benefits of binary search trees, but we want to make sure in the worst case the running time is not very large. Then we're obviously going to have to make some adjustments to the height, and in order to do that we're going to have to change the insert and maybe the delete operations to do a little bit of cleanup to maintain the shape of the tree. Well, we know from our analysis of decision trees that if we have a binary tree with n nodes, then the height must be at least growing like log n. On the other hand, we know that if we have a tree which is very close to balance, such as, for example, the left complete tree we used to construct a binary heap, that for such a tree, very easy to see that for such a tree the height is in fact order of log n. So for a binary search tree, it is possible, provided we reorganize the shape of it after it gets a little bit unbalanced because of insertions and deletions, it is possible to have a tree of the right height, in other words, order log n. The question, of course, is going to be how much additional work are we going to have to do to keep it like that? So what sort of cleanup might we be talking about? Well, suppose you have a tree that looks roughly like this. Got some kind of subtrees hanging off here. Let's give them names. And it might be that the height here is just more than we want. We want to kind of shift these ones up, and we don't mind shifting this down slightly because the maximum of all of them will actually get smaller, or it will get no bigger. We can afford to sacrifice some height here to reduce it here. One of the basic ideas is what's called a rotation. So what we're going to do is start with this tree, and we're going to kind of rotate it that way so that this node now becomes the root. So it still has this subtree hanging off it, but now its left child, instead of being this tree, it's actually going to be this. And now B, subtree B, can't be going off that one anymore because that node has now moved up there, and in fact it hangs off that one. Now there's a couple of things we need to notice. First, look at the height. What's happened to the height of the tree? Well, this part over here, this height of this left part, let's say, increased by 1. The subtree B, any contribution to the height there hasn't changed. And with C, it's decreased by 1. So what we've seen is that we decreased by 1 here, we've increased by 1 there, we haven't changed there, and that might be something good. If C happened to have a much larger height than it should have, so for example, this is 7 and this is 3, then we're going to get 4 and 6, and overall we've improved the height of the tree. So that's the basic idea of a rotation, and there's a symmetry in binary search trees, so you can also go the other way. So from here you can rotate that way and get here, but you could also start here and do a rotation the other way, so that now this becomes and you get back to the original tree that you started with. So that basic operation of a simple rotation is actually the key to rebalancing binary search trees, and there's a huge number of different classes of trees which basically combine these kind of rotations in different ways and have different rules for when you need to trigger them, because each time you do it is some sort of cost, right? The next thing we have to think about, which is perhaps even more important, why does this rotation work? It works in the sense of reducing the height, possibly. But how do we know that what we've got is still a binary search tree? That's absolutely key. So we have to check that. But it's not too bad. Everything here in the C is larger than this root, and it still stays the same. So we don't have to worry about that. So everything that was smaller than this shaded node, namely these two, are still on the correct side. Now what about B here? B, it's larger than, the keys here are in fact larger than these ones, but they're smaller than these ones. And again, it's on the left side with respect to this node. So everything is working well there. You can look at the other cases as well. You see that everything maintains the correct order with respect to the other nodes and subtrees. So this is a legitimate operation which will just change the shape, but give us a nicer shape in some cases. So for example, if you had a horrible looking tree that was this shape, and you just inserted something and it got pushed down to there because it had to. For example, you're doing them in alphabetical order. You first insert A, then E, then I. You might want to rebalance that with a rotation, and it's easy to see what you will get when you do that. Using the method we looked at above, it'll look like that, which is a perfectly balanced one. Now you might not want to do that every time you insert, but you should do it some of the time to avoid extremely bad performance. And as I said, there are very many types of what are called self-balancing binary search trees. Now the self-balancing, it's not going to be helpful if it turns out that this kind of rotation is very expensive. You would hope at least that a rotation like that can be done in constant time. Well, it can. All you're doing is reallocating some pointers, right? Nothing's changing here. This here has to go down to there now, and this has to then point to that instead of that one. There's only a constant number, in fact, of pointers that need to be changed. Everything inside these subtrees stays the same. It's just these small number here that need to be rewired. So each particular rotation is a constant time operation, and you just have to arrange it so that you're only doing a relatively small number of such rotations when you do your rebalancing. And the analysis can become quite complicated. So I'm not going to go into details of exactly how each class of trees does the rebalancing and how often. But the idea is that they do only a constant amount of work, and they rebalance infrequently enough that they really don't make the running time worse than you would hope. So what we're hoping is that we can rebalance these trees so that the worst case we can have order log n for the height. So we can always do insert, find and delete in order log n time. And it turns out that we can for various classes of trees. We're only going to discuss one class of these trees right here, and it's the historically first class of self-balancing binary search trees, which was introduced in 1962. And these are called AVL trees. So what are they? An AVL tree is a binary search tree which always maintains an interesting property. It's that if you look at the height, say, of the left subtree, and then you look at the height of the right subtree, they're not too far off. The basic condition is that the height of the left subtree and the height of the right subtree are no more than 1 away from each other. Since one of them could be larger than the other and we're not sure which one, the condition is that the absolute value, the difference of the heights, is less than or equal to 1. So they either have exactly the same height, or one is higher by 1 than the other. Okay? Now, in order to maintain that, there's quite a bit of work required. Suppose this tree's got larger height than this one, then if I try to insert something here, it will and it comes to the bottom naturally by ordinary binary search tree insertion, it will have height 2 more than this one, and so immediately I have to do some kind of rotation procedure. On the other hand, here I might not need to worry. A key point that I didn't explain perfectly earlier on is that not only does this property of heights have to hold for the whole tree, it has to hold recursively all the way down the tree. So you pick any point, this could be anywhere in the tree, not just the root of the tree, and then if you look at the subtrees below that, they must all have this property. So it's very well balanced all the way down, but it could look like something like this. So here's a tree, I don't know, this is going to have a height 2, for example, and let's get a tree here with height, let's say 3. If I look at the root, this left subtree's got height 1, and this has height 2, so that's okay. If I look here, I've got height 1, 0. Here I have 1 and 2, 1 and 0. Go through all the cases, that would be an acceptable AVL tree. But something like this would not be. It satisfies the property everywhere down here. Everything here is okay. There's not too much imbalance between subtrees, but when you get to the root of the whole tree, something goes wrong. Left subtree has height 1, right subtree height 3. Violates this property of being an AVL tree. As I said before, I'm not going to go into all the details of the running time, how many rotations are required and exactly which ones. You can look those up if you're interested. But we should at least check that such trees, which do look very balanced according to the definition, have in fact the correct height. In other words, if the height of these trees is not order log n, then it defeats the entire purpose. So the argument here will be similar to the one we've seen when we talked about decision trees and a lower bound for sorting. We want to show that an AVL tree of a certain height has a reasonably large number of nodes. In other words, a tree with a fixed number of nodes has to have a reasonably small height. So I'm going to let A sub h be the minimum number of nodes in an AVL tree of height h. And let's suppose we have a tree here which has height h and in fact has the minimum number of nodes for that height. It's an AVL tree. Its left and right subtrees are also AVL trees because of the recursive definition of the balance property. If the balance property holds everywhere in the tree for every node, then it certainly holds for smaller trees, subtrees of the original tree. So in other words, I have an AVL tree here, which has got the smallest possible number of nodes for its height, and I've got 2 AVL trees here, which are the left and right subtrees. Notice that since I want the smallest possible number of nodes for the height, whatever the height of this thing is, and this one, I might as well ensure that these are as small as possible. Okay, I can replace them by smaller ones if necessary, even keeping the height the same. So in other words, I can assume that this tree that minimizes the number of nodes, it also is minimizing the number of nodes in here and in here. So in other words, A sub h, the number of nodes in this full tree, is 1, which is the number of nodes in the root, plus the number of nodes in the left, plus the number of nodes in the right. Each of those trees being minimizing trees. Well, it's certainly at least as big as what we get when these are as small as possible. Now, how can these be as small as possible? The height of the whole tree is h. That means one of these trees has to have height h minus 1. The other one could be smaller, but it can't be too much smaller because of the balance property here. In fact, it could only be one smaller. So the absolute smallest number of nodes we could have here is 1 plus the number you have in a minimizing tree of height h minus 1 plus the number of you have in a minimizing tree of h minus 2. And in fact, it's easy to see that that's in fact the equality. It's not just an inequality. If I have a minimizing tree of height h and height here and h minus 1 here, or vice versa, I will get an AVL tree of height h, and you can't get a smaller one. If I had two things here of height h minus 1, I would certainly get more. So in fact, you actually get equality over here. And this recurrence has some initial conditions. If you have only 0 height, you've just got a single root, so you've only got one node in the tree. And if you have height 1, then the smallest number of nodes you could have in an AVL tree of height 1 would be 2. You could also have 3 if you had one here, but that we want to find the minimum number, so it would be 2. So this recursion here, with those initial conditions, is what describes AH. Now you look at that, you'll see immediately that it looks very similar to the Fibonacci recurrence. And by very similar techniques to those that you use for Fibonacci recurrence, you can show that AH is greater than or equal to some C to the H, where C is bigger than 1. In other words, it grows exponentially. In fact, C is more or less the same value that you get when you do the Fibonacci recurrence, namely the golden ratio. It doesn't really matter. The point is it's growing exponentially with H. So even though you might not be getting like 2 to the H, you don't get perfectly balanced tree where everything doubles at every level, it grows fast enough as you go down because of this balance property that you actually get an exponentially large number there. Now finally, we just want to show that if we have any AVL tree with n nodes and height h, what's the relationship between n and h? Well, n has got at least as many as a minimizing tree of that height, so it's at least as many as that. And if you take the binary log, you're going to get that log n is greater than or equal to h times log c, which is some constant. In other words, the height is less than or equal to some constant times log n. So AVL trees are in fact pretty balanced, have nice height, just as we expected intuitively from the definition. So as long as you don't have too much overhead in terms of the rebalancing rotations that we mentioned before, it should be a good idea to use self-balancing binary search trees to implement dictionary, where you need to have good control over the worst case for your basic operations of finding, inserting and deleting. That's the takeaway from this lecture. So here we are at the questions again, only a few this time. First thing to think about is that there are a lot of different types of self-balancing binary search trees. What I suggest is that you look on somewhere, for example, Wikipedia, see how many there are, and browse a few of the classification. Look at the article on AVL trees and you'll see all the details of how and when rebalancing is done in order to maintain the nice AVL property, and an explanation of how often you're doing that and how much work is required. But there are many other types of them, and you should certainly look at red-black trees because that is a very popular class. Related to this, do some looking around on the descriptions of various programming languages. You can search for that online. You'll find the specification for, say, C# or Python or various languages like that. Try to see which type of self-balancing binary search trees they use when it comes to implementing dictionaries. In fact, they're all going to use something like that. Okay, so that's a bit of internet research required. Work on that, and we'll see you next time.